move now to the next talk, which is about predictive maintenance. And the title is Towards Predictive Maintenance Strategy through Waveform Anomaly Detection Using Unsupervised Learning. And the talk is given by Jun-Ting Lin from Lawrence Livermore Laboratories. Let's play the video, please.
Hi everyone, my name is Tim Lin. I'm from Lawrence Livermore National Laboratory, and today I'll be talking about our work on waveform anomaly detection using machine learning. And the goal is to build a predictive maintenance strategy for a seismic network. So the motivation of this study is that we have a gigantic network, the International Monitoring System, and we need to ensure the data are in good quality for event monitoring purposes. So the station maintenance is very important. However, station maintenance is very expensive as it involves money, time, and human effort. And also, if you look at the plots over here, you can see that those are the scheduled maintenance. And not all of these are associated with the actual instrument failure. So for example, if you look at the time series plot over here, these are the 30 days of continuous time series data. And you can see that it's not associated with the instrument failure. So the question is, can we make the maintenance more effectively? So there are basically three types of different maintenance strategy. And the first one is called a run to failure. And you can see that this is the original data quality. But over time, the instrument degraded, and then eventually we have this failure and the data loss. So that we have to go to the field and fix the problem and bring this data back to the original standard. And the second one is called the preventive maintenance, and this is also called the scheduled maintenance, and which ensure the data is always in good quality. But however, they are perhaps more servicing than the actual needed. And the last one, which is our goal, is called predictive maintenance. And the idea is, if we can detect this subtle degradation type of signals, and then we can make a plan beforehand, so that we are not too late to have data loss, and also we can save some money for the unnecessary maintenance over here. So there are, however, challenges in detecting degradation signals. And the first is that the anomalies can be anything. There's no clear definition if you look at the figures. And also the signals may be subtle and hidden within the data. So without telling you that this is a anomalous signals, it's very hard to tell from just looking at the time series data. And the way that we know this is true is to compare it with the neighboring station, and we see there these missing signals over here. And also, there's no ground truth data to learn or to compare. So we propose to use this unsupervised learning model, the autoencoder model. And the idea of autoencoder is that it compresses this information into a lower dimensional space. And then a decoder will decode this information back to the original waveform. And by training the model with a lot of seismic data, it learns what are the most important or the common features that needed to represent seismic data. And we can compare the input and output using the correlation coefficients. So we can use this value as a proxy of the data quality. And the good things about this structure is that there's no assumptions on anomaly signals. And also we can explore the information in seismic waveform. So we train the model with the USMS data. And we basically download 8 years of continuous data for all these networks. And then we downsampling it to 1 Hertz and cut that into in hourly chunks. And we split more than 5,000 days of time series data into the training, validation, and testing data sets. So after training, we can now test the model performance you can see that this is a result when the model's testing with the normal seismic waveform. You can see that the fitting is quite good, and the correlation coefficient value is higher than the other signals. And the figure on the right shows that their distribution. You can see that for normal data, it's basically have a higher CC value. And for the anomalous data, we are expecting have some lower CC values. So this is how we can apply it to continuous data sets. So this is the example of the 1 day, 24 hours of continuous measurements. You can see that we cut it into a 1 hour chunk. And the blue one is the model input, the red one is the model output. And the small text over here shows their CC value, which is the proxy of the data quality. And you can see that for some anomalous waveform, the CC value is low, and for some of the normal waveform, the CC value is high. And we can do that for a longer term. This is 8 months of continuous data for the Alaska station, the IL-15. You can see that there is a sections, the duration is about 1 month, where the CC value is significantly lower than the other time period. And if you look at the time series data, this is the 30 days of continuous time series waveform. You can see that it's actually something wrong for the sensor. So that's 8 months of time series data. And if we apply the model to even a longer term, so this is 8 years of continuous time series data for the same station IL-15, we see there's a seasonal variation not associated with the actual sensor problem. So after remove that, the bottom figure shows the residual, which is pure the data quality. And we see that there's a sensor degradation type of signals, which lasts for about 2 months and until the maintenance visits, which brings the data quality back to the original level. And this suggests that it's very possible that we can identify this in the very long term beforehand, so that we can make the maintenance plan earlier and to avoid the potential of data loss. We can also compare our model to the baselines. So the DL is our deep learning autoencoder model, and the random forest and logistic regressions, these are supervised machine learning models. So in order to train the supervised machine learning models, we need to provide some example anomalous waveforms in order to train. And this one is the traditional QC detector. It's called a Ch1 tool. And so you can see that for the performance on the station IL-15, the Alaska stations, they all have the very similar patterns. So which makes sense because these are the known types of anomalies, and the supervised machine learning model is specifically trained to learn this data. And also for the PYC, these anomalies are obvious to be detected. But in the case if we have a new stations or a new type of signals, and this is when our model outperforms the baselines model. And this is the example of the YKAR3, the Yellowknife array in Canada. And you can see that our model detects something that is completely missing by the other models. And the way that we can validate this is true is to compare the neighboring stations. So this is the, you can see that the YKR3 is basically missing some detailed waveforms over here and there. And also this is the daily time series waveform is changing the amplitude response. So this is something that is unknown type of anomaly and is not built in our original training data sets. So which suggests that our model has the flexibility to learn this new type of anomaly signals. And next, to understand our model performance in a more statistical way, we can do something called confusion matrix. So this is something that we can do to classify the different cases: the true negative, the false positive, the false negative, and also the true positive. And and after that, we can calculate their accuracy. So for our model, we got a pretty good accuracy of 88%. Compared to the others, the supervised learning model has the highest accuracy because it's specifically trained with those provided examples. But it has less generalization capability to new type of signals, as the slide showing earlier. And for the traditional QC approach, it still needs some tuning to for the case of the long-term anomaly detection task. So we further test the model's generalization capability using the GSN station, the Global Seismograph Network, which is a completely different seismic network with various different types of sensors. And you can see that without retraining, the model can already get an accuracy of 80%. So this suggests that the model is generalized and it can be easily applied to a new sensors or some new data without significantly retraining. So which is good. And here's some example that the model can be directly applied to other IMS data. So this is the example for the Yellowknife array in Canada. You see that the model successfully detects about the 3 weeks of the anomaly. And if you look at the time search data, you see there's some the digitizer noise over here. And also this is the example of the NORSAR array, and the model successfully detects about 6 months of data anomaly until the maintenance visits. It brings this data quality back to the original level. And you can look at the time search data plots. There are some strange signals over here. And also you can look at the Warramunga array. This is in Australia. And the model successfully detects about 6 months of data anomaly. And if you look at the time search data, it's very hard to identify from the raw time series data. And the way that we know this is true is to compare it with the neighboring stations. So you can see that it's missing some signals over here and there. So which suggests that there's something wrong for this station. And it is hard to be detected if we just look at the time series data plot. So in conclusion, we propose a deep learning autoencoder model to detect anomaly in continuous time series data. And by using this, we can detect some long-term anomalies, which allowing for the more efficient development of maintenance plan. And also the performance, it's very similar to traditional approaches when the anomaly signals are explicit and well-defined. And our unsupervised model has the capability to discover anomaly cases that were not present in the training data sets. And also, this approach has the potential to be expanded to other types of sensor, for example, infrasound. So we recently published the results in SRL, and unfortunately, I won't be there for the live Q&A sessions, but always feel free to reach out to us if you have any question. So thank you very much.
Thank you very much, Junting, for a very interesting talk. Unfortunately, Junting is not online, so he will not be able to answer any questions.